his own measurement apparatus, ran an observing program by himself for a couple of years, targeted 61 Cygni, the flying star, and measured a distance to it using the parallax technique. That was 1838, folks. That was over 200 years after Tycho Brahe raised his objection to the sun-centered universe idea. Someone finally did it. Now, Friedrich Bessel wanted to communicate this result to the public. He wrote a journal article, all that, but he knew the public might be interested. We finally know how far away a star is. Big deal, right? So he wrote a newspaper article to be printed in newspapers around the world. And he wanted to communicate how far away this star is in a way that people could grasp, that they could hang on to. And he found that all the units and adjectives and everything were just, coming up short. So he coined a new word. He coined a new term to describe how far away this star was. 61 Cygni, the flying star, is pretty far away from us. But he invented a word, light year, to describe how far away the star is. 61 Cygni, the flying star, is about 10 light years away from us. It takes light 10 years to travel from that star to us. To give you a sense of what 10 light years is like, remember Tycho Brahe freaked out at the thought of the stars being 700 times further away than Saturn? 61 Cygni, the flying star, 10 light years away from us, is 70,000 times further away than Saturn. And it's one of our nearest neighbors. And the first person to measure it, ever, was Friedrich Bessel. Now, over the course of the 1800s, astronomers did what astronomers do best, which is copy each other. And they measured parallax distance to star after star after star after star, slowly expanding our view of the universe from 10 light years to 100 light years to 1,000 light years to 10,000 light years. Our universe was getting big, and it was getting weird. A lot like Portland, I'm told. Among the weirdness that astronomers saw up in the night sky were these cloudy, fuzzy patches called nebula. Nebula is a Greek word meaning cloudy, fuzzy patch. All sorts of weird stuff. Now these nebula, man, no two were alike. They came in all sorts of shapes and sizes and colors and structures. It was nuts. Astronomers had no clue what was going on in the late 1800s. They're just collecting data and saying, I have no idea what's going on. And they stare at the night sky, find someone else, I have no idea what's going on. I mean, astronomers today do the exact same thing. But, they were still doing it in the 1800s. Of particular interest in the late 1800s was a certain kind of nebula. A kind of nebula, right here, these sketches were made in 1877, by the way. A kind of nebula called the spiral nebula. The spiral nebula were very cool and very pretty and very freaky. You can actually see a spiral nebula. There it goes again. Sorry, folks, it's running. Nope, there it is. You can see a spiral nebula with the naked eye. It's in the constellation Andromeda. It's called the Andromeda Nebula. How handy is that? It's pretty big. It's about the size of an outstretched fist, and it's fuzzy and spirally. It's a spiral nebula. Now, here's a photograph of the Andromeda Nebula taken in 1900, and you can see why astronomers would be really fascinated by this. I mean, look, you got this bright core, you have these dark lanes, you have the spiral features, you have around 11 billion stars. It's just a weird thing, right? No idea what it's made of, no idea why it has this shape, no idea how far away it is. How far away is it? Well, we tried the whole parallax thing on it. Didn't work. So obviously it's more than 10,000 light years away. But how far? 15, 25, 100,000? I didn't say 100,000. You said 100,000. It wasn't me. It wasn't me. How far away is the Andromeda Nebula? You didn't know. They didn't know. The problem was in the late 1800s, the early 1900s, this whole parallax technique It was tapping out. You know, you build a giant telescope, you have the best precision instrument, you have photographs. It can get you to about 10,000 light years. It can't get you any further. You need a new technique. You need a new trick for measuring distances. I'm going to teach you the next trick that we learned to measure distances. Let's say I want you to measure the distance to my phone. So you break out the angles, you do all that, you try the whole parallax thing, and you're like, no, I don't, it's too far away. I can't use parallax. Okay, so let me do you a favor here and illuminate the situation. That's an astronomy joke. Can I get a pity laugh or something? Thank you. You guys are great. Portland's great. So I turned on my flashlight. How does this help? It doesn't.
No.
So what? Now it's bright. Okay, how far away is it? You still don't know. But I'm curious. I'm curious if anyone in this room, don't let me down, if anyone in this room has the exact same phone that I do. Does anyone have a Samsung Galaxy S10? S10, that's right, I got a new phone. Book's doing well. You got an S10? You got it with you? I saw a nervous hand go up. Do you have it with you? Can you pull it out? All right, we have a Samsung Galaxy S10. Can you turn on your flashlight? You gotta swipe down and then it's a button that looks like flashlight. Here we go, we're gonna do it. I'm assuming you're not lying. Yeah, it takes a while to get the flashlight going. Oh, there it is. Okay, check it out. We got two Samsung Galaxy S10s here with their flashlights on. I'm going to teach you how to measure the distance to my phone. You ready? Step number 1, put the light in front of your face like this. Okay, you good? Step number 2, take out a ruler, measure the distance to your flashlight. Okay, good. Step number 3, take out your brightometer and measure how bright the flashlight is. That's a scientific device, folks. I'm a physicist. You can trust me. Okay, so you know the distance to your flashlight, and you know how bright it is. Now, you take out your brightometer, and you look at my flashlight. My flashlight will be a little bit dimmer. Why? Because it's further away. But you know how bright it's supposed to be. Because you have the exact same phone that I do. If you have an iPhone, this isn't going to work. If you have a Samsung S9, this isn't going to work. You have different flashlights. You don't know how bright this is supposed to be. You only know how bright this is supposed to be if you have one right here. So you can compare how bright yours is, how bright mine is. You can compare the brightnesses. You can do a little bit of trigonometry. You can calculate a distance. This is called a standard candle. A standard candle. If you know for sure how bright something is in the sky, then you know how far away it is. Now, despite their names, Samsung Galaxy S10 are not distributed throughout the universe, but nature did give us some standard candles. Nature gave us some standard candles in the form of something very, very messy and unpredictable. There's a certain kind of star out there called a Cepheid variable. Guess what Cepheid variables do? They vary. They get brighter and dimmer. Whoop-de-doo. All right. Some Cepheid variables are really bright. Some are really dim. Some change brightness over the course of a few days. Some change brightness over the course of a few weeks. It's a mess, right? In the early 1900s, a wonderful astronomer by the name of Henrietta Swan Leavitt, the only astronomer with an animal for a middle name, in case that comes up on trivia night, did something amazing. She discovered a relationship. She found that the longer it takes for a Cepheid variable to change brightness, the brighter overall it is. And the faster it switches between bright and dim, the dimmer overall it is. This means You can look at a Cepheid variable. You can watch it change in brightness over the course of a few days or a few weeks. Once you've measured that, then you know how bright it's supposed to be. You can compare that to how bright it looks. You can do some trigonometry, and you can calculate a distance. You have standard candle. This discovery unlocked the universe. Because the Andromeda Nebula, in the early 1900s, we discovered had a couple dozen Cepheid variables inside of it. And another astronomer by the name of Edwin Hubble, using at the time the world's largest telescope, measured these Cepheid variables, watched them change in brightness, converted that to a true brightness, compared that to how bright they're supposed to be or how bright they looked, did some math, calculated the distance. And he discovered that the Andromeda Nebula is not the Andromeda Nebula, but it's the Andromeda Galaxy. And it sits 2.5 million light years away from us. That was 1924. 1924. About 100 years after Friedrich Bessel exploded our view of the cosmos, Edwin Hubble did it again. The universe became far larger than we ever thought possible. Overnight, with one paper. Over the course of the 1900s, astronomers did what astronomers do best, which is copy each other. Very good. Told you you're all astronomers now. And they measured distances to galaxies. They made maps of the cosmos. Galaxy by galaxy, measuring its position on the sky, calculating a distance to it, measuring some properties of it, moving on. One by one by one by one. These surveys continue to the present day. Here's one of them. It's called the Sloan Digital Sky Survey. It's at Apache Point in New Mexico. It is a mapper of the cosmos. It is a galaxy survey instrument. Now I'm going to show you what we have revealed to be the modern day map of the universe. It's a little bit overwhelming. So we're going to take some baby steps, okay? We're going to go start from some, maybe some large structures that you might recognize and might identify, and then we're going to go out. We're going to zoom out. So we're going to start somewhere potentially familiar. I'm just curious, does anyone recognize this particular large structure in the universe? Oh, come on. Anybody? Anybody? No, do you guys have football out here? Or is this just a Midwest thing? Okay, this is the shoe. This is where the Ohio State Buckeyes play. It's a big thing. Fits like 120,000 people. We have nothing better to do in Ohio. But it's a large structure. It's a big thing. Look. You can zoom out. Yeah, see, I told you it's big. This is Columbus. This is North Campus at Ohio State. There's my former office. Okay, it's pretty big. If we zoom out more, can you still see the stadium? Yeah, of course you can see. It's right there. It's the little baby stadium right there. It's so cute. Oh, whoops, sorry about that. I don't know what that is. It's right there. That's the other Buckeye Stadium. The practice stadium. That's our experimental cornfield. Don't joke, the University of Illinois, where I went to grad school, we literally had an experimental cornfield. Right in the middle of campus, true story. Okay. It's there, right? It's there, you can see it. But, it's kind of small, but Columbus is big. Columbus is a decent city, I guess, according to some measures. Can you spot Columbus? Yeah, I put it in the middle of the slide. It was kind of handy and convenient there for you. Cities are big. Columbus is a decent city. There's Cincinnati, there's Cleveland. Pennsylvania is actually very low resolution if you actually visit there. This is not an artifact. It's just how it is. Can you guys still spot Columbus? Oh, it's right there. Oh, yeah. You're like, yeah, that's totally what I saw. I was pointing right at it. Can you guys see Portland?
Yeah.
Yes. Here? There? Look, there? There? I'm so bad at this. I'm so That's I was at Seattle, but you're south of Seattle and you're north of San Francisco, right? Very good. I'm a cosmologist, right? This is too small scale for me. That's my excuse. All right, but okay, so my point is the Earth is big. The Earth is big, right? I mean, come on, we're the biggest of the rocky planets. We've got liquid water. We've got an atmosphere. I mean, we got a strong magnetic field. Life is pretty good here, right? Right? Yeah, okay. Here we are. Let's point it right at there we are. Okay, but the sun is big. Yes, there are bigger stars, but most stars are smaller than the sun. Most stars are smaller than the sun. It's a big star, right? Here's a typical nebula. Each one of these dots is a star. A typical nebula has enough material to manufacture around 10,000 suns. One nebula. Here's our best guess as to what the Milky Way galaxy looks like. We're one sun, one star, one solar system. Milky Way galaxy is home to around 300 billion stars. Our nearest neighbor star is not Barnard's star, it's Proxima Centauri. It's about 4 light years away from us. The entire Milky Way galaxy is about 100,000 light years across. That's one galaxy. That's our home. This is our home. We live on a small spur of one of the spiral arms out in the suburbs, about 2/3 of the way out from the galactic core. It's nice here, crime rate's low, we got good schools. It's not so bad. Besides, rents are crazy in the core. So. Okay, so I'm going to show you a movie. This movie, it's made by the Sloan Digital Sky Survey, that telescope I showed you earlier. This movie is actually out of date. It's like 7 years old. Only has 500,000 galaxies in the movie. But it's going to start in our nearest neighborhood with the Milky Way and our nearest neighbor Andromeda, and it's going to zoom out. It's going to pull back further and further and further. It's going to reveal the universe as we currently understand it. Keep in mind, each one of these dots that you see is an entire galaxy, home to hundreds of billions of stars. The distances between any two galaxies is a few million light years. So we're pulling back into the tens, the hundreds, the thousands of light years across. This is our universe. And one of the most amazing things we see when we start to build maps of our cosmos is that galaxies are not scattered around randomly. No, there's a pattern here. There's a structure here. Can you see it? Let me show you a little picture. There's long filaments. See these long filaments here? There are these dense knots that we call the clusters. There are these vast empty regions that we call the voids. Tens of millions of light years across with absolutely nothing in them. This is a structure, this is a pattern. We call this the cosmic web. The cosmic web is made of galaxies, the same way your body is made of cells if your body was 100 million times larger than it is. The cosmic web is the largest pattern found in nature. It literally fills up the universe. This is what we get after centuries of asking, how far away are you? Starting with a comet in 1577, this is what we get. We get a map of our universe. We get this cosmic web. We get the greatest structure we've ever observed in all of science, right here. We're not done mapping it. This is less than 1% of all the galaxies in the observable universe. And what's more, not only is the universe almost incomprehensibly vast, it's also alive. You see, Edwin Hubble not only found that the galaxies are actually galaxies and sit at vast distances away from us, he found a couple years later that they're moving. Planets move, stars move, entire galaxies move. And on average, the galaxies are moving away from us and away from each other. Over time, the distances between the galaxies grows. Our universe is expanding. Our universe, our entire universe is getting bigger every single day. And this fact, this observation completely changes everything about what we understand about the universe. Because if the universe is expanding, it's changing, it means it changes with time. It means the universe was different in the past, and it will be different in the future. Just like your lives. You were different in the past, you will be different in the future. You have fond childhood memories. Our universe remembers a time from before the first stars. You anticipate with dread old age, decline, and death. Our universe is dying. I told you it was going to get dark. You change and grow and evolve with time. Our universe changes and grows and evolves with time. Our universe itself is alive at the very largest scales. So what are we supposed to take away from that? We've been asking questions of the night sky for hundreds of years. Big questions, important questions, meaningful questions, questions about our very existence. And we've learned some things. We've got some answers. We didn't necessarily like those answers, but we got them. We learned that the universe is vast and cold and empty, and we are cosmically insignificant. That you could wipe away the Earth, you could wipe away the solar system, you could wipe away the entire Milky Way galaxy, and the march of cosmological evolution would go on completely unchanged. So is that the ultimate answer? Is that what we learned, that we're insignificant, that we don't mean anything at all? I don't think so. I don't think so. Because yes, we learned that the universe is vast and cold and empty and uncaring. But we learned something else. We learned that it's messy and unpredictable and chaotic. That it's no different than our lives down here on Earth. We're a part of it, right? And this unlocks something incredibly powerful. It means that yes, the universe is chaotic and messy and unpredictable. Life on Earth is chaotic and messy and unpredictable. But we're a part of it. We're all a part of the same universe, which means that anything we do learn, any pattern or law or physics that we are able to uncover here on Earth applies throughout the universe unchanged, because we're all a part of the same thing. That physics, that science is universal. I mean, think about it. The same gravity that pulls an apple from a tree is the exact same gravity that keeps the planets in orbit around the sun. Completely unchanged. It's the exact same force. A hydrogen atom in your drink tonight behaves exactly the same as a hydrogen atom on the far side of the Milky Way, 100,000 light years away. Unchanged. You understand a hydrogen atom here, you understand a hydrogen atom 100,000 light years away. The force, the electricity that keeps your heart beating is the exact same force that illuminates the cosmos for us to understand it. Unchanged. We've been asking questions in the night sky for hundreds of years. One of those questions is, what's our place? Where do we belong? Well, in this case, the answer has come back crystal clear, folks. We ask the universe, what's our place? Where do we belong? The answer comes back right here. Thank you so much.